Hello everyone, I'm Adrian, and in the following minutes I'll be presenting our novel approach that improves from multiple perspectives and supervised embedding learning with memory banks. One of the key aspects that led to the explosion of deep learning methods in over the past decade was the availability of large labeled datasets such as ImageNet. However, we can only label so little. In practice, we are surrounded by virtually unlimited amount of unlabeled data that we miss out. Ideally, we'd want to use as much of this as possible, especially that we as humans construct our understanding of the world from significantly fewer annotated signals. To address this, unsupervised and self-supervised representational learning emerged as a popular direction, the goal of which is to learn a set of useful representation without using human-provided labels that can be easily adapted to other tasks unknown during training. From a high-level perspective, it is achieved using a pretest task that provides pseudo-labels at train time. Popular pretest tasks include colorization, with the goal of predicting the colors given an input grayscale image, rotation, that consists in predicting the angle of an artificially rotated input image, data reconstruction using autoencoders, in painting or incompletion that attempts to predict parts of a signal that were dropped, and so on. Of particular relevance to this topic is instance-wise classification that treats each image in the dataset as a separate class. While the instance-wise classification can be implemented using a normal classification layer with C outputs and a cross-entropy loss, as the number of instances grows, this becomes unfeasible, especially in scenarios where we have a continuous data stream. To address this, a non-parametric softmax and contrastive losses-based approaches were proposed. The main idea is to minimize the intra-class variance while maximizes the inter-class one by comparing the target positive samples against a set of negative ones formed by the other samples in the batch in the left figure, or by the ones stored in a memory bank in the right figure. Depending on the case, a memory bank can contain the entirety or a portion of a dataset. Building on this, herein we propose to improve unsupervised contrastive learning with memory banks, making the following contributions. We propose a large mini-batch for memory bank contrastive learning by pulling for each sample a set of k augmentations within the same batch. We show that this approach leads to stronger networks and improves the memory bank representation. By having a set of k augmentations at our disposal, we introduce a simple consistency loss which enforces the lodges obtained by different augmentations of the same sample to be close enough. Notably, it is achieved without trying to enforce discrimination with respect to the negative samples as proposed by previous approaches. Finally, we observe that instance discrimination is not meaningful for samples that are too visually similar. Hence, we propose a hard negative mining approach for improving the memory bank that gradually merges extremely visually similar data samples that were previously forced to be apart by the instance-level classification loss. Our approach improves upon the state-of-the-art by up to 6% on CIFAR10 and up to 3% on STL10. In our proposed large mini-batch with multiple augmentations, each instance within the batch is augmented k times and passed as input to the network, producing n times k embeddings. The final scores are produced by taking the inner product between the future embedding fi and the representation stored in the memory bank. Similar shades of the same color denote augmented versions of the same instance. The memory bank is updated by taking the average of each instantiation of the same instance within the batch. As we can notice, increasing the number of augmentations per instance from 1 to 4 offers a 4 to 5 performance uplift on the CIFAR10 dataset. Similar effects can be observed when measuring the cosine distance between the representations stored in the memory bank at adjacent epochs. Taking advantage of the previous formulation where multiple augmented copies of the same instance are present within the same batch, we propose to enforce a consistency loss between the positive samples. More specific, giving a set of multiple instantiations of the same sample within the batch, generating by applying a set of randomly selected transformations, we enforce the product's embedding to be similar between themselves using a KL consistency loss. This can be also seen as a form of subdistillation. As the result shows, up to 1% gains can be obtained on CIFAR10. Finally, one downside of instance-based classification is that very similar images could be forced to be apart. To elevate this, we propose a multi-stage hard negative mining that gradually groups together and merges such instances based on a cosine distance. By gradually merging the instances using an offline process, we can improve the performance by up to 2–3%. Here we can see an example of 3 instances merged into one. Notice that our method typically groups together similar types of objects that undergo various perspective transformations. The plots next to the images correspond to the pixels the network attends towards, classifying the given sample correspondingly. The maps are computed using the noisy gradient integration method of Sundarajan. Note that our method learns complex concepts focused on the object of interest. When evaluated on the product dataset, as the results show, our method outperforms all prior work by a noticeable amount. Similar results can be seen on STL10 and CIFAR10 datasets. With this, my talk concludes. Thank you for your time, and if you have any other questions, please pass by our poster session or reach out via email.